Please take your seats. Excellent. I'll keep an eye on that. We have two talks in this session. Our first talk is an invited talk from Alberto Donati, who is a research scientist at CADA, the Center for Applied Internet Data Analysis. Alberto's been doing a lot of work with his team on routing security, or shall I say routing insecurity, over the past many years. It's still a topic, it's still a thing, and he's been making hay on that. Today he's going to talk to us about detecting and neutralizing BGP hijacking. This was a paper, I think it appeared in CCR. It's going to also be presented at SIGCOM.
It's under submission to TON,
okay.
And you can find the paper on archive.
It's very good. We read it, and we invited Alberto to come talk to us. So thank you.
Thank you. Thank you for inviting me. Good morning. So this project is called ARTEMIS, and it's a joint work between CADA and Inspire Research Group at Fort at University of Crete. As I was saying, the paper is on archive. You can access it through the program of the workshop. The paper is extremely dense, with lots of results and experiments and contributions, I would say. So I will go very quickly and just try to give you some insights, and I hope that you will be interested in reading the paper. I'm assuming that the topic is well known to this audience, BGP hijacking. So basically when an attacker is stealing or manipulating your BGP routes, and the traffic diverts from the original route, and it reaches an attacking autonomous system. In the simplest case, then the attacking autonomous system could even be able, in some cases, to send traffic to the legitimate owner of this prefix, and therefore position itself to carry out a man-in-the-middle attack at a large scale. So we call these man-in-the-middle hijacks. And here is the mandatory slide that you can picture in your mind with all the latest news headlines, big names, panic, and I've been a bit lazy, but there have been so many events. So last week, there's been lots of hype about the BitCannel hijack factory shutdown. A few months ago, you heard about the Amazon hijacks. There have been many events reported over these years. I think that's scary, but what is also scary is that certain attacks can be carried out in a much more stealthy way, in a more sophisticated way, and we should care also about those. In general, we should care about the fact that any autonomous system on the internet is still vulnerable to this problem. BGP has a trust problem in the sense that it trusts anybody, basically. So, of course, the ideal solution is proactive, is deploying RPKI. Last year, and this one we published it on CCR as an editorial, we published the results this year of a survey that we did last year with more than 70 operators participating, asking them about BGP security, routing security, the solutions that they have been taken and why not. And for example, about RPKI, unsurprisingly, we found out that RPKI is not widely deployed because it's not widely deployed. But I don't think this surprises the crowd here. Well, other reasons were high complexity, high cost, and anyway, we have to deal with this reality. So RPKI is taking some time to take off. In the meantime, we're left with some reactive solutions. They're basically based on third-party services. So we inquired operators also about these services that some of them use, how satisfied they are, what are the problems in terms of, practical problems. And we studied these approaches, and unfortunately, they suffer from several issues, starting from comprehensiveness, because most of them are focused on only very simple attacks. For example, when an attacker is originating the prefix of someone else, and not on attacks in which the attacker is manipulating in a more clever way the forged announcements. So another big problem of these approaches is accuracy, which is a problem, unfortunately, by design. They are prone to false positives and false negatives because of practical issues, because the operator that uses this kind of services needs to constantly update information about its network, which autonomous systems are supposed to announce certain prefixes, at which level of aggregation, which autonomous systems are their neighbors, and so on. And this doesn't happen consistently, let's say. It doesn't happen continuously. And therefore, then there is the problem. If it doesn't happen often, then either the third-party service will generate false positives, or it will have to be tuned in a more conservative way, and therefore it will generate false negatives. This has another effect, has effect on then what's the actual result in terms of defense of the actual mitigation. We are interested in detecting these events because then we want to mitigate them, right? And because the accuracy of these approaches is very low, then the operators end up manually verifying about the attack, sending emails using the good old phone. And as you see also from the results of our survey, in several cases, often these attacks have an effect on the networks for even more than a day. And we're talking about massive traffic, interception, manipulation, and so on. And the final issue is, another one is privacy. Operators often are not comfortable in sharing information about their network, their policies, and so on. So with Artemis, we try to address these issues by proposing a radically different approach, which is not a third-party based approach, but it's self-managed. So the idea is that an operator protects itself by running Artemis on their own network, on a server in their own network, or this server can be hosted in the cloud and connected through a separate channel to your network. And what it does, it runs the Artemis approach, and basically it uses as input data feeds from stream of BGP data, for example, from projects like RouteViews and RightBreeze, and information, of course, from the local routers, the routers of the network that it's protecting. And you can imagine that it might take information from a route reflector, for example. And then the other input that it uses, it's a configuration that can be tweaked by the operator, but ideally, we would like this configuration to be automatically, the opposite, to be automatically updated using the information from the local routers. So this is quite of a paradigm shift. And magically, we spent lots of people worked on this project, and I would still call it work in progress. But we found that this way we were able to address all the 4 issues that I mentioned earlier. So with Artemis, actually, we are able to cover basically all types of attacks. We include sophisticated attacks, and accuracy in several cases is fantastic because we're talking about 0% false positives and false negatives, basically by design, because we are using the ground truth, the knowledge from the network that the operator is operating. And in the remaining cases, 0% false negatives, or the ability to work on a trade-off between false positives and false negatives at the expense of an increased latency. And of course, as I was saying earlier, with accuracy then comes speed. If you can trust the alerts that are coming from your system, then you can think about automating some reactions and automating mitigation. And in the paper, we show with experiments on the real internet that with Artemis, we can mitigate hijacking attacks within a minute. Actually, it happens also in few seconds. And finally, the problem of privacy, which is intuitive. In this case, all the information stays within the network, is not shared with a third party. Okay, so basically Artemis is based on BGP data. And it's based on the intuition that today, the so-called public monitoring BGP infrastructure, the infrastructure operated by projects like RouteViews, RightBreeze, Colorado State University BGP Mon, that are sharing BGP feeds, it became so pervasive, today is so pervasive, that it allows to have great visibility into what happens in the internet. We're talking about hundreds of monitors. Another important aspect that inspired us is that these projects are transitioning into a live streaming mode of sharing feeds. And therefore, we can start conceiving approaches in which the operator leverages this data for near real-time detection. So in the paper, through simulations, we actually performed some extensive simulations using data from the real internet topology, at least what we could infer of the real internet topology, and AS relationships, inferred AS relationships, and the data about the location of the peers of the collectors of RouteViews and RightBreeze, which in the rest of the talk I will call simply monitors. During these simulations, we actually showed that by using all the monitors of route fuse and write breeze, it's possible to observe all attacks of those that we simulated with a significant impact. And by impact, and so you want to look here, basically by impact, we measure impact in terms of percentage of autonomous systems that in our simulation in the internet got polluted by the routes forced by the hijacker. And I think I should hurry up because time is short. As I said, this is kind of an advertisement for the paper. You find more information about impact and speed in our simulations. So we try to see how far, inspired by this aspect, right, and we try to work on this approach, then we try to see how far we could push it. Could we really tackle all the possible attack configurations? And we found that it was hard to do this analysis also of related literature without a detailed taxonomy. So in the paper, we propose a BGP hijacking attack taxonomy, which is based on 3 dimensions. The first one, we call it type 0, 1, 2, is based on where the attacker is placed in the path. So if the attacker is actually originating the prefix, we call it a type 0. If the attacker places itself 1 hop from the origin AS, the legitimate owner of the prefix, then we talk about type 1 and so on. Then another aspect is which prefix is announced by the attacker. Does it announce the exact prefix that the legitimate owner is announcing? So it's an exact prefix hijack or a sub-prefix, or is it announcing space that is owned by another autonomous system but is not even announced? And then we talk about squatting in the case. And finally, we looked at how does the attacker behave and what is the impact on the data plane, let's say, but this also affects the control plane actually. So is the traffic dropped and so it's black holing? Is the attacker trying to impersonate the victim, or is instead placing itself as a man in the middle, as I showed in one of the first slides? And this has an impact on how different detection approaches work. So I cannot go in details. Again, in the paper, you will find more information. There is an analysis of related work with respect to the taxonomy that we have come up with. But actually, what you can see here summarized in the table is that Artemis basically covers all the types, all the attack configurations. That are, anyway, all the attack configurations. One thing that I wanted to add here is a mention for iSpy, a paper that was published, I think, at SIGCOMM 10 years ago. That was also self-managed hijacking, BGP hijacking detection, but it was based on data plane, and some data plane techniques do not operate well, cannot operate in certain scenarios, and cannot operate with certain types of attack configurations. So Artemis, I think it's the first self-managed approach for BGP hijacking that is based on control plane, exclusively on control plane data. So as you can imagine, if you own all the information in near real time about the network, most of the detection becomes trivial. And this is what we're showing here for a large class of attacks. Basically, by design, we have 0 false positives and 0 false negatives because we know exactly what are our neighbors, even what are our neighbors. So even type 1 hijacks can be detected with no false positive or negatives. However, there is a part that is not trivial of the detection. There is one case that is left. I don't think I have much time to talk about it, but it's basically the case in which the attacker is actually faking a link in the path, and it's faking to be adjacent to a neighbor or a neighbor of a neighbor, but in the best case scenario for the attacker, to a neighbor of the originating AS. So it's actually a fake link 2 hops from the origin, and it must be an exact prefix hijack because otherwise we would detect it as a sub-prefix directly, and so we wouldn't have problems. So we had to come up with a 2-stage approach in which the second stage is optional. There is a long section in the paper about this detection approach. But in a couple of minutes, what it does, it checks, it monitors the appearance of new links for the address space that is monitored, so for the prefixes that are announced by the AS that it's protecting. And when it detects a new link that it hasn't seen before, it looks in a history, by default, the last 10 months of history, for any AS path, for any prefix that is seen, and it checks for the appearance of this link, but in the reverse direction. And so here you can see the link ASX, ASY, where SY is actually a neighbor of the origin AS. And then we look in the history and we look for the link in the opposite direction. And here the assumption is that this must have been announced by ASY. So it's true that it exists in the topology, a link between ASX and ASY. Things are a bit more complicated. The attacker might be able to fake, to pollute the history by using a second bad autonomous system, another malicious autonomous system, or it could be able to do it by actually generating an announcement with a loop, which instead can be easily filtered. Actually, things are even more complicated because in some cases, the attacker might be able to do this to still pollute the history without appearing twice or using a second twice in the same announcement or using another AS. But these are special cases. There are only certain cases in which this is possible. Basically, the attacker is pretending that there exists a link between an AS that it's adjacent to. Again, so a link between ASX and ASY, an AS that is adjacent to the attacker. So because of this also special case, we have an additional restriction. We check all the autonomous system numbers that appear on the left of all the paths in the history that show the link in the opposite direction. If there is a common AS, we still mark it as suspicious. I know that this is very fast, but you can find all the formalization in the paper. We have lots of Greek co-authors, so there are lots of Greek letters in the paper. It's fantastic. So I invite you to read the paper. But another aspect that is interesting about this approach is, okay, how does it work in practice? So we did also extensive emulations. We actually ran Artemis stage 1 for each single autonomous system that in March 2017 on the internet was announcing prefixes. So pretending to run Artemis in 40,000, 50,000, I don't remember the number, autonomous systems. And this is the firewall. Should I deny this one? You guys should tell me. Okay. And we used history from the last 10 months, and we ran this for 30 days. Again, for each single AS originating prefixes, and using data from all the route views and write monitors. So we're talking about more than 400 monitors. So what the blue line is telling you here is how many times these ASs running Artemis in emulation would have seen a new link appearing. So this is one new link per day. This is one every 10 days. And the red line is telling you how many of these links would have generated an alert. And so, for example, if you check the point that we have highlighted, in this case, 73% of the autonomous systems running Artemis saw less than one suspicious event every 3 days, which still you might think it's a large number. These are still alerts, right? So that's why we came up with stage 2. In stage 2, what we do is we trade latency. We wait a little bit after we detect this new link, by default 5 minutes, and we trade this for additional information. And there are 3 aspects here that are important. One is that actually there is the intuition that if this was actually a real new link that appears in the topology, giving some time to BGP to converge, we would start seeing in some cases the same link in the opposite direction. And actually this happens. So at least in simulations, because this is something that we couldn't, we found that it happens in reality, but it's just a 1% for the route views and write monitors. In simulations, we found what we actually expected, that the data from the local routers is really precious to see these links in the opposite direction. The other aspect is that by waiting a little bit, we can estimate the impact that the attack has had. So because we can see which of the several hundreds of monitors of route views and RIS have seen that polluted, not polluted, that suspicious advertisement. And so announcement. And therefore, we can use this information to change the policy for the alerts. For example, we can decide to treat differently alerts that have had a very small impact. And that's what the operator can configure, for example, only for certain prefixes in Artemis, to have a different reaction for alerts that are apparently have had a smaller impact. So basically what we can do is to trade removing a lot of false positives for introducing some false negatives with potentially less impact. Again, same type of emulation. Here, what you want to see is that in the black line, we consider basically all the alerts that have, even for events that have been seen by a single monitor of route use and write-please. And when you switch to the colorful lines, then you are moving for alerts seen at least by 2 monitors. So the message here is that the majority of the unverified new links from stage 1 that pass stage 1 are actually seen by only 1 monitor. And then, for example, if you look at the blue line, what you see is that, which is alerts that have been seen by 3 or less monitors, then you would see that for 81% of the autonomous systems in our emulation, they would have not seen a single alert in a month. Finally, I hope I have another 30 seconds. Mitigation, I haven't talked much about it. It's of course important, as I said. There are 2 approaches that we propose in the paper. They're inspired by approaches that have been discussed, have been proposed before. The first one is actually do it yourself. It's just deaggregate your routes. Unfortunately, you can do that only down to /24 level. /25 wouldn't propagate on the internet. The other one is, okay, relying on other autonomous systems to announce your route and tunnel them back to you. And I think an interesting result of this analysis, unfortunately, this one could have been done only in simulations. We're still trying to convince Akamai, Cloudflare, VeriSign, if they are here, please come talk to me, to do some experiments in the real internet. But what we've seen is that these operators are actually very well positioned to fight BGP hijacking attacks. These are operators, sorry, I didn't say it. It's written here, but these are the guys who perform DOS mitigation by BGP hijacking, benign BGP hijacking. They announce your routes, they take your traffic, they scrub it, and they tunnel it back to you. Imagine doing the same thing for BGP hijacking. You just have to remove the scrubbing phase, but it's exactly the same thing. And actually, the simulation suggests that they would work well than the tier 1 operators. Okay, one last word about Artemis. There is an open source tool that we are working on. Partially, this is sponsored by the RIPE NCC community projects in 2017. So stay tuned. The tool hopefully will come by the end of this year. And with this, I conclude my talk. And if you have any questions, be happy to try to answer.
Thanks. We have time for a few questions. It looks like we have someone coming up right now. Please identify yourself as well. Thanks.
Of course. Hi, I'm Jared Mach from Akamai.
Hi.
I think one of the things I assume is an underlying premise here is that you actually know what you're announcing.
Yes.
And you can actually document that somewhere or somehow.
Yes.
And in my experience in working with networks, the operators often do not know a complete inventory of all of their assets of IP space, believe it or not, and they don't necessarily know what the origin AS or the AS path that's expected should be. And so I'm wondering, if you don't know that, how well this type of a tool would work.
Please forgive us, we're scientists. No. I've heard that, and that's interesting, and I think that's a problem of its own, first of all, that operators should try to solve or address.
Of course.
Indeed, this is marked as one of the challenges, the automated, what we call the automated configuration. We started discussing this with some operators. One thing we can imagine is we're trying to work on scripts that would take data from route reflectors and start populating the configuration. I know that things are much more complicated in large operators networks, so another option is also to monitor the data and have it then collecting it automatically and then have a human in the path that kind of verifies this thing. That would be an opportunity for the operator to start putting order in their network as well.
Yeah, I mean, yeah, we took a similar type of approach internally where we built a BGP monitoring bot that looked at similar type of data sources and for the expected paths. So yeah, this looks very cool. We should talk afterwards about the other Akamai piece.
With pleasure.
Lovely. One more question. Thanks.
Hi, I'm Rachi, UMass Amherst. So I was wondering about the DOS mitigation technique that you mentioned toward the end.
Yes.
Is that with like AS path poisoning or AS path prepending? I was curious about what exactly you meant there.
I don't think I said prepending. So you want to know more about how this approach would work?
With the DOS mitigation
So basically, these operators, when they try to protect their clients from an attack, they announce the same routes. So they do a kind of benign hijack of the routes of the victim. They attract their traffic since they have multiple locations from which they can announce these prefixes. And so what we show here, that basically they are able to prevail with respect to the attacker because they can propose shorter paths to the BGP engines. And then what they do is they scrub the traffic, and tunnel it back to the victim, right?
It's like some kind of interception.
Yes, some kind of interception, I would say so.
Okay.
And the idea is that same mechanism could be used to just fight somebody hijacking your routes without the need to do scrubbing. Of course, you need to have a channel with enough bandwidth to communicate with the victim. So an idea would be to at least peer at some IXP collocation facility. Does it answer your question?
Yeah, I'll talk to you some more later.
Okay,
Thank
sure. Thanks.
Okay, let's thank Alberto.
Thank you.
Thank you very
Thanks.
Our second and final speaker of the session, standing between us and lunch, is Andreas Reuter.
Test.
Perfect. We can hear you. Andreas is a first-year PhD student at the Freie Universität Berlin. He also completed his master's and his bachelor's in computer science there as well. Andreas is doing some really interesting work on monitoring internet exchange points and internet backbones for security incidents. But today he's going to be talking to us about a different topic, which is measuring the adoption of RPKI. So thank you very much.
Thank you for the introduction. So this is joint work with Randy, Ethan, Italo, Thomas, and Matthias. And for those of you who don't know what route origin validation is, let me just give you the brief background. So it pertains to BGP, the same problem that Alberto just told you about. You're probably all aware. So in BGP, there's no mechanism that allows people to check whether an AS has permission to originate a certain prefix. So for example, in our test situation here, we have AS A and C. They're both originating prefix P. The arrows show you how the announcements propagate, and now ASD needs to decide which route to choose. What ASD doesn't know, I guess this thingy doesn't work. Yeah, well, I'll just use the keyboard. All right, what ASD doesn't know is that ASC is an attacker, ASA is the legitimate origin, and since BGP follows AS shortest AS path first, in the absence of an overruling policy, the traffic will go to the attacker. So that's the problem. We already have a solution for this. It's called the RPKI, the Resource Public Key Infrastructure. This is a specialized public key infrastructure that allows resource owners, and the resource here is an IP prefix or autonomous system number, allows them to get a certificate that attests to that ownership, and then they can use their certificate to create an authorization object to allow specific AS to legitimately originate their prefix. So in our example, we have the owner of prefix P creating an authorization object to legitimize the originating ASA. And now ASD can do route origin validation using this information and can know that attacker C has an invalid route and ASA has the valid route. And if there's no authorization objects, just for completeness sake, it says not found, which is the case for most prefixes. So that's route origin validation. And now the question is whether ASD wants to use this validation result to, for example, drop invalid routes. So that could be one possible policy. Could also say to depreference invalid routes or anything else. Okay, so just some definitions. I mentioned these authorization objects. They're actually called route origin authorizations, ROAs. So they are cryptographic objects. They authorize exactly one AS to originate a set of prefixes. And then we have route origin validation, which is a BGP router validating incoming routes. But this does not include acting on this. So this has to, the result of that needs to be used in the policy to actually do anything. Okay, so our research problem now, or our goal is, we would like to find out whether there are any AS that are actually using ROF-based filtering policies. And the motivation for that is threefold. I mean, first of all, we'd like to assess the current state of defense on the internet, because common wisdom suggests that no one is doing this, and we'd like to know if that's true or not. Once we have a methodology to measure this, we can also track deployment over time. We can attribute spikes in deployment to certain events and possibly improve deployment. And maybe if we give people a list of AS that are actually filtering, this will create an incentive for other people to at least look into this and perhaps deploy it themselves. And the challenge here is, of course, we need to infer private router configurations with measurements. All right, so this is a quick definition slide just from the same page. So whenever I talk about BGP data or I show like a topology or something, we always take data from route collectors. A route collector is a BGP speaking device that collects updates from BGP routers and dumps them periodically. A vantage point is a BGP router that peers with a route collector and sends updates. So Alberto called this monitors, I'll call them vantage points. So we should have synchronized, but oh well. And I'm not going to draw the route collector in the pictures. So this is always implied when there's a topology, it's from the point of view of one vantage point. Okay, now on to actually measuring route origin validation. There are two principal approaches. Existing work has used uncontrolled experiments. What I mean with that is they take existing BGP data from route collectors, they take existing ROAS, and they use heuristics to infer which AS is filtering and which is not. And this can be done fairly quickly because it only needs existing data. The problem with this is that it doesn't work, and it can't work. I'm not going to go into detail why it can't work. If you'd like to know more about this, the paper that this talk is based on was published at CCR this year. There we go into detail, or we can talk offline. So what we are doing is controlled experiments. So this involves actively announcing our own prefixes on the internet, actively creating our own ROAS. So of course, this is a bit slower and cumbersome. We need to actually conduct experiments. We need an AS, first of all, and need our own IP prefixes. The AS needs to be reasonably well connected. So this is a pretty high barrier. In our case, we are using the peering testbed, which is a BGP testbed where researchers can experiment on the internet. So yeah. We are conducting multiple experiments to measure this with different goals. So I'm going to only talk about the basic one, which has the goal to find an AS or find any AS that filter invalid routes. And when I say find an AS that filter invalid routes, I mean an AS that at somewhere in its network has deployed route origin validation. They don't have to be filtering all invalid routes they receive. It only has to be some filtering going on. That's kind of our goal. And this experiment is, the core is very simple. We announce two routes. One of them will be valid, one of them will be invalid, and then we see how people react to that and infer who's filtering or not. So on the BGP side of things, we announce two prefixes. We announce PA, our anchor prefix, and we announce PE, our experiment prefix. You can probably already tell by the names that PA is going to be the control variable. We're not going to change this. PE is going to be experiment variable that we're going to play with. And these two prefixes are, at least on our side, treated identically. They have the same route object in the rear database because some folks filter on that. They have the same length, obviously. We announce them at the same time to the same origin and from the same origin to the same peers. So we hope that other AS will treat them identically as well. Okay, on the RPKI side of things, we actually conduct the experiment. So initially, we issue ROAS for both prefixes so that the announcements will be valid. We wait until this propagates throughout the internet, and vantage points have chosen routes for both prefixes. And throughout the experiment, the anchor prefix will always stay valid. Well, its announcement will always stay valid. And for the experiment prefix, we now start periodically changing the ROA, so the announcement flips from valid to invalid back to valid. And we're doing this on a 24-hour cycle. So each experiment is contained in one day, and then we can run them each day and have this longitudinal experiment going. And then there's essentially two types of situations that we run into when we analyze the data. One is that we are directly peering with an AS that has a vantage point. So in this case, we're on the right. This is the peering AS. And we are announcing both prefixes directly, and the vantage point adopts the direct route. You can tell by the color that both announcements are valid. This is the initial situation. Now we flip the ROA for the experiment prefix. And one observation that we've made is that there's no route anymore for the experiment prefix, which pretty conclusively tells us that the vantage point must be filtering. Just for completeness sake, in this image, we're peering directly at the vantage point. But this also works, this reasoning also works if we peer with any other router in ASA, because we're not trying to figure out whether a specific router is doing ROF. We're trying to figure out if an AS is doing this somewhere. So the reasoning still works here. The other type of observation we made is that there's still a path, but it's an alternate path over a third AS. In this case, this also tells us that there must be filtering going on at the vantage point or in the AS, but clearly they're not dropping all invalid routes. They're doing it selectively. So This is something we've actually observed. One explanation for this might be that ASX is a provider of ASA, and the policy is to always accept anything from a provider, but filter invalids from a peer. Right. So the other type of situation, the more common type, is that we are not directly peering with the vantage point AS. So we have at least one AS in between us. And again, the initial situation is similar. The vantage point adopts the same route over ASX for both prefixes. They're both valid. Now we flip the ROA again. And similar as before, the path is gone. That's one observation we made. And the other observation, similar as before, is there's an alternate path. The problem that we have now is that this introduces ambiguity. We know that someone must be filtering based on ROF, but we can't tell who it is. It must be either ASA or ASX, or it's both of them. So this is the problem. The question is now, how do we solve this? Because this is quite a limiting constraint on our experiment reach, right? We can only, like most arrays, we're not directly peering with. So unfortunately, the solution is try to establish direct peering with the vantage point AS, and then we're back to the first type of situation where we can reliably determine whether they're filtering or not. Or we can check if the intermediate AS has a vantage point and then do the same type 1 situation again. So obviously, these are not very scalable solutions. So this is a problem with our approach. For the AS that we can measure its reliable results, for those that are too far away from us, yeah, this is a problem. Okay, so now on to results. We've been doing this for about a year, more or less. Before October 20th, we had found 3 AS that drop invalid routes. None of the big ones. It was a small Italian ISP, it was a small ISP in the UK, and it was a Dutch networking initiative. And on October 20th, something happened at AMP6. The AMP6 route server offers a feature where it essentially filters out invalid routes for its peers if you so choose. And this used to be an opt-in feature, and now it's an opt-out feature. They changed this on October 20th, and our algorithm picked this up, and all of a sudden had over 50 AS that now drop invalid routes. And as a side note, I mean, this is not technically, these AS have not deployed route origin validation. This is a route server doing this for them, but the route server is transparent on the BGP level, so we're technically counting this as long as we keep in mind what is actually happening. And M6 is also not the only IXP to do this. I think France IX has done it, NL IX I think as well. There's also a small IXP in Costa Rica that's been doing this for years. Unfortunately, the peering testbed is not peering at these exchange points, so we don't have to reach to pick that up. Fortunately, it is peering at the M6, so that's why we saw it. We also know of at least one major European IXP that is gearing up to do this, and I'm sure there's other IXPs as well. So yeah, it looks like it's getting traction. Okay, so now that we've been doing these experiments every day for a year, we thought it might be a good idea to make these results public, to give the community the means to assess the deployment themselves. So we launched rof.rpki.net. You can check it out right now if you like. This is essentially just a big table. Each row in the table is for an AS, and for an AS that we think is filtering invalid routes in some capacity. We update it daily, and for each AS, you can click on the details on the left, and then you'll see which vantage points we're actually measuring, when did we last measure them, when did we last think they were filtering, yeah, and so on. So we appreciate any feedback on this. So if you have an AS that's filtering, that's not on the list, it might be because we're not in your reach, or you're not in our reach. If you have an AS that's on the list and it shouldn't be on the list, then you should email us and we can talk about it. One last thing is, I've mentioned the limited reach of our experiments, so this is obviously a little bit annoying. We have 180 or 190 AS that we can actually reach. Many of those are big ones, so if they do start measuring, we'll see a big impact. But we thought maybe we can enhance this with data plane measurements. And the idea is very simple. We just use something like RIPE Atlas, and we trace route towards our prefixes. And if we see that there's a successful trace route to our anchor prefix, and unsuccessful trace routes to our experiment prefix when the routes are invalid, then we know something's doing rough on the path. I mean, it's still ambiguous who's doing it, and the analysis is it's not as easy as it sounds, but this is one way to kind of improve the reach of the experiment. And so far, we've done this. This is a work in progress. We've done one measurement campaign on the data plane with around 200 AS. We have found none additional AS that filter. This also might be, though, that we have the problem of false negatives, since an AS might filter, but the trace route still goes through because of a default route. So there's not much we can do about that, at least not at scale. So this is just something we have to live with. All right, so now to conclude, control experiments are crucial to measuring the adoption of rough-based filtering policies. There are some AS that do rough-based filtering. Before October 20th, 2017, we found 3. There might be more out there. Actually, there was an email a few days ago on the NANOG mailing list where someone reported that there's at least 2 commercial IXPs that have enabled it now. Unfortunately, we can't see that with our experiments because they don't have vantage points. So there's at least some people are doing it. And after October 20th, the number spikes up because of the route server deployment. And again, this is getting traction at other IXPs. So this might be a good way to boost origin validation deployment. Yeah, that was the last point. And lastly, I would like to ask everyone very nicely to please consider peering with the peering testbed, which is incredibly useful for researchers that don't have access to ASs or IP prefix elsewhere. And of course, also peer with route collectors, because these are insanely useful, not just to researchers, but also to operators. So please consider doing this. And if you'd like to know more about the methodology and our experiments and why uncontrolled experiments don't work, this is all in the paper. CCR January issue this year. All right, that's it.
Okay, thank you. Thanks. We have time for a few questions. Any questions? While you all are thinking of questions, I'll pose one for Andreas. Very interesting work. It's very interesting you're able to detect whether or not people are performing these checks or not. I was wondering, in cases where you saw the checks being enforced, do you think you could use that to perhaps detect the use of this for adverse purposes, censorship, or other things? I'm reminded of Sharon's work on the use of potential misuse of these for causing routers to filter or drop prefixes that they might otherwise accept. You think your tool would currently support that kind of measurement, or?
If I understand correctly, I think this would be more appropriate to do on the RPKI level, to actually check out who's being revoked and who's being issued certificates. And I mean, if we do have a scenario where everyone does RPKI, everyone drops invalids, and to find out censorship, I think it would be easier to look at the certificates and the ROAs that are being issued.
How do we get more people to deploy?
People need to fix their stuff. I mean, we already, in our retro slide, we saw the reasons why people don't use RPKI. I think one easy thing would be if people just started to not mess up their ROAs, because right now there's a negative incentive to deployment, because if you filter invalids, you might lose connectivity to actually legitimate ASs or legitimate prefixes, which is bad. So people just get on that. There's a lot of invalid routes that really shouldn't be invalid.
Did you see any patterns in the ASs or regions or ISPs or types of networks that were doing this properly?
I think the classic error is that I think someone has messed up the maximum length field in ROAs.
Okay.
I don't know if this has a bias to the region or AS type. It's just, I don't know why this is such a big deal or a problem.
Oh, I do actually. I have a draft on that.
Perfect.
That slider
Okay.
ops this afternoon, in fact, about max length. So, yeah. Sharon Goldberg. One quick question that I just completely forgot. Oh my God.
It happens.
Okay, here it is.
Yeah.
So, traditionally when people ask about RPKI, I hear people saying that they're not going to validate because they're nervous about invalids that are incorrect. And if you look at the NIST RPKI monitor, you see some fraction of the results of the RPKI causing things to be invalid that shouldn't really be invalid. And I always thought, my mental model was people are not going to drop invalids because they're afraid that they're dropping something they shouldn't be because it's a bug. So my first part of my question is it true that people are no longer afraid of this? Or is it the case that the invalids that are wrong are so irrelevant that nobody cares? What's going on with this? Is just my mental model completely wrong?
So if I understand correctly, why is deployment picking up now?
No, I mean, we know that the RPKI sometimes causes things to become invalid when they shouldn't due to misconfigurations. And this was preventing people from turning on route origin verification for a long time. So what's happening? Is this change? Is this no longer true? People no longer worried about this?
I think they're still worried about this. I think it's getting better, though. I mean, I think over time, when RPKI first started, there was a larger number of invalids that were just misconfigurations. That's been going down, but they're still there. So I think it's slowly getting better, and more people maybe trying to make the leap. One additional thing that prevents people, I think, is also the implementations. Some of them aren't that good. So we've tested a few of the implementations, and we found at least one major vendor that did not reevaluate routes when they changed RPKI state. So if you went from valid to invalid, they wouldn't notice that. And you'd have to withdraw the route and re-announce it, and then they would get it. And later on, we found that even that didn't work. We had a case where we would announce a route, it was valid. The validation would say valid. Then we would withdraw the route, change the rollout to make the route invalid, re-announce it, and the same router still said it's valid. So this is pretty bad, and I think it's being worked on, but I think that's definitely a reason why people might be hesitant too.
Randy Bush, IJ. Sharon, about 3 years ago, Pam Paper, Daniela Iamartino, who compared route views announcements with the RPKI longitudinally and ran the actual algorithms and found many of the, quote, invalids get overridden by more specifics or whatever, and that the number of actual invalids that would be dropped is very small. And so maybe some of the operators accidentally read that paper.
Job Snyder's NTT. The number is today roughly 2,200 prefixes. It is indeed small, but it's not small enough for an operator like NTT to enable origin validation. So to this extent, I will reach out to the RARs and ask Ripe and Aaron to email their customers and members saying, hey, either delete your ROA or fix the ROA, one of the two. So I hope that we can bring down this number to more acceptable failure rates.
Good. Just could you identify yourself for the rest of us in the room? Thanks.
Job Snyder's NTT.
Thank you. All right, we've got 4 minutes. We could improve adoption, or I guess we could have lunch. Any takers? Okay, let's thank Andreas for a great talk. Thank you. Oh, Matt has one quick announcement, everyone.
Yeah, the lunch is in the adjacent space. If you have not registered for the ANRW, either by paying to attend the IETF and registering for ANRW, then the lunch is not for you. So at least wait 20 minutes and then go and see if there's any food left. Otherwise, if you have registered, please go next door and have lunch.
Thanks, Nick. Sure thing.